Power screws are essentially jacks. I want to jack up a load, I use a screw jack. And the technical term for them is power screws because I'm applying some power to them as opposed to just holding something together with a fastener. So this depicts a typical screw jack, at least schematically. So I have a screw with a particular type of thread on it that happens to show what's called an Acme thread. That's the one that the Roadrunner always buys, right? And you see a roller bearing in there serving as a thrust washer so that the very heavy load P that I'm lifting doesn't give me a whole lot of friction where the nut turns against the ground. So I could use this by turning the screw and making the nut move, or in this case I'm turning the nut to make the screw move. So we show the nut in gray. It's got some kind of a handle on it that I can grab and turn around by hand and just make the screw go up. And it'll lift quite a very large load because I've got a very high mechanical advantage potential here. In essence, it's an inclined plane. I'll show you a picture of that in a moment. But this slide depicts the various standard thread forms that are used for this application. And the simplest is the square thread. Easiest, well, I guess it's not all that easy to make to get it exactly square, but it's certainly simple. The lead is defined as the distance the nut moves in one revolution, which is also, unless it's a multi-start thread, equal to the pitch, which is the distance from one tooth to the next, or one thread to the next in this case. Acme thread is in the upper right. That has an angle of 14.5 degrees per side, or 29 included angle. That makes it both easier to manufacture and also gives you a good wide base. And then the third, and that will take a load in both directions. Both of those, square and Acme, will allow loads in both directions. If I only have load in one direction and I want a stronger thread, I can use this buttress thread, which is like an Acme, but it's skewed. So I have a bigger root dimension to support the load with lower stress, okay? So you very rarely see square threads except in very cheap jacks. More often you'll see an Acme. Once in a while a buttress. So this depicts the inclined plane I was referring to a moment ago. A screw of any sort is nothing more than a ramp wrapped around a cylinder, creating a helix. So if I unwrap the ramp from the cylinder, I get a linear plane, yeah? And so this is physics 101. You know, I want to push a heavy load, I want to raise it, so I shove it up in a inclined plane, and I need less force over more distance. Force times distance is work, and I get large vertical force and short vertical distance, and the energy is equal. Work done equals energy, right? So that's the basic principle. Simple as that. So I have the lead, which I mentioned a moment ago. It's shown here. That would be the distance that the nut moves or the load moves in one revolution of the nut, or the screw moves, whichever way you want to think of it. That lead has a lead angle called lambda, which is just the rise over the run. And the run is pi times the pitch diameter, circumference of the pitch circle. Very much like gears, same terminology. We have a friction force in the plane of motion here. We have a horizontal applied force F, which is of course tangential. We have a load P and a normal force perpendicular to the plane. Over here we have the angle of the Acme thread, alpha. And that of course would be 0 for a square thread, something else for a buttress.
TU is the torque to lift the load. TSU is the torque in the screw, and TC is the torque due to the collar friction.
And P is my applied load, dP is the pitch diameter, mu is my coefficient of friction, pi dP is my circumference, L is the lead, and alpha, of course, is this angle over here. And this is the component from the washer. P times dC over 2. dC would be the diameter of this bearing down here. and its radius is half of that. So that's force times radius, which gives me a friction at the nut. Now, if I don't put a ball-type bearing on this thing, most of my energy is going to go into turning that nut against the ground plane. If you buy a real cheap jack that will probably not have a ball bearing in it, it will just have a plain bearing, and they're very hard to turn. So a good quality one will have some kind of rolling element bearing between the nut and the ground plane, so you don't lose all of your friction there. You have enough friction developed in the threads as it is. This plot you see here defines the efficiency, which is the W out over W in, which is PL over 2 pi T. T is your torque, P is your load, L is your lead. And this is plotted against lead angle and expressed as a percent, so it's non-dimensionalized. And the sad fact is that Acme threads typically have a lead angle down in the 2 to 5 degree regime, so they're down here. And you can see that the lead angle has a very distinct and nonlinear effect at both ends, because as I approach 90 degrees, it's not going to move very well either for the lead angle, and 0 is down here. So at these low lead angles, the family of curves depicts the coefficient of friction, which is usually considered to be about 0.15 as a pretty good coefficient, steel on steel. If I can get a lot of lubrication in there and get it down to, I almost have to be hydrodynamic to get it down to 0.01, then my efficiency goes up. But realistically, I'm probably in this regime of 0.15, and down at 5 degrees, I got like 40% efficiency. And that's about as good as it gets. They rate these things as a table I didn't put into the slide that shows typical efficiencies based on lead angle of the screw, and they range from 18 to 36%. So they're horribly efficient, or they're very inefficient, I guess is a better way to say it. And that's just the nature of the beast. One advantage this type of jack has is it can be self-locking, by which is meant that I can't back drive it. So load on the screw will not make the nut turn. Yes?
Can ball screws have a low enough coefficient?
Yes. Yes, I'll show you a picture of a ball screw in a minute. And a ball screw has ball bearings running on the threads, and those will back drive usually. So I need the friction to make it not back drive. In fact, that's the factor. If we look at the equation, this simply tells you what it is here. If I want to jack my car up, I think I don't want a back drivable screw, right? Because as soon as I stop turning the handle and let go, down it comes on my foot. So I need it to stay where I put it, so I want a non-back driving screw for that kind of application. Any place I have to hold a load. And it's a function of the coefficient of friction versus the lead angle, lambda, and the cosine of alpha if there is any. So a square thread, cosine of alpha would be 1. And for a square thread, as long as the coefficient of friction is greater than the tangent of the lead angle, it won't backdrive. So if I get the coefficient too low so that it's less than the tangent of lambda, which is what happens with the ball screw, because I'm deliberately making the coefficient low by having balls running around in there, then I become a back-drivable screw. Very easy to determine what situation you have if you know what the coefficient of friction is and your lead angle and the angle of the Acme thread or whatever. This would be, alpha would be 14.5 degrees for an Acme thread. Here's the ball screw. So it's quite a clever device. Notice the threads are a different shape altogether. They're sort of round in the bottom to fit the balls. And the balls are in this crazy track. There's actually like 2 sets of them here. And they're circulating around in the grooves, but then they have to get back home from where they started, because this is a closed track. So there's a return tube up here, so that when the balls finally get through the third of the grooves here, they come across and feed back in on the other side. These are typically not self-locking. But they have high load capacity, sometimes bigger than a conventional screw because they've got a lot of balls sharing the load in here. And they don't have stick slip because rolling type elements tend to have a static and a dynamic coefficient of friction that are just about the same, which is, I described to you the issue with the ball bearings in old trains when they finally got rid of the sleeve bearings on train wheels, which ran in boundary lubrication, by the way, most of the time, and they substituted ball bearings. They suddenly didn't need two locomotives to get the train started from a dead stop. And what they would do in the old days is they would use the two locomotives to get it rolling, and they would shut one locomotive off to save fuel and go on their merry way as long as they were up at speed and had kinetic energy stored until they got to the Rockies, and they had to cut the other engine back in to get over the hill and so forth and so on. These are used a lot as positioners, as more for positioning than for creating loads. You don't use these as a jack, obviously, because they don't self-lock. But you'll see them used in machinery where I simply want to move something back and forth in a straight line and control it fairly accurately. They're precision ground. The balls are tight tolerance. So I can get pretty accurate positioning down in the thousandth of an inch or half a thousandth range over a foot. A typical spec for accuracy for these things is like half a thousandth of an inch per foot. That's pretty good. And I would typically drive them with a servo motor so I can hold position. That gets around the non-self-locking. So if I'm lifting a load with the ball screw or pushing, creating a force with the ball screw, and I tell the servo motor to hold position, it's powered up and it just stops, and that keeps it from back driving. Of course, if the power fails, it's all over. That's a big disadvantage of servos, by the way. If you have a machine that's entirely servo driven, which is quite common nowadays, and you have a power failure, everything starts to coast to a stop, and things can get out of phase. So you have crashes with parts of machines running into other parts of machines because it's not being brought down to a controlled stop with the phasing all maintained, as opposed to a cam-driven machine, which are the predecessors to servo-driven machines, where your timing is mechanical because all the cams are on a common shaft and they're locked to a key, and so whether the shaft is rotating or not, everything is in proper phase. So when I lose power on a cam-driven machine, it coasts to a stop, but everything comes down together and I don't have any crashes. So if you were trying to use a servo and a ball screw to position something and the load was such that it would move the thing if it didn't have power, you need to have some kind of a safety device in there so someone doesn't get hurt. That's about all I'm going to say about power screws. The focus today is going to be more on fasteners. Fasteners are kind of a fascinating, no pun intended, topic. It seems mundane. You know, you talk about the nuts and bolts. Who cares about the nuts and bolts? That sounds kind of uninteresting. But the truth of the matter is, the design job is not done till you've taken care of the fasteners. And there's some very interesting engineering goes into both the design and also the specification of fasteners. I'm going to talk about that in some length today. This is just showing a collection of some of the variety of fasteners. And you know from your own experience there's hundreds of different types and styles of fasteners you can buy that have very specialized applications and whatnot. Self-tapping screws, self-threading screws, screws for plastic, screws for metal, you name it. I just show a very limited selection here. We have bolts, also called cap screws, socket head type. I don't show a hex head. They're very common also. Socket flat head, socket button head, nuts in various flavors here. Standard hex nut, the thickness is a fraction of the diameter, somewhat close to 1, I think. The hex jam nut is made thinner, often used in combination with the regular hex nut to literally jam the two together. One of the most effective ways to prevent threaded fasteners like this, bolts and nuts, from coming loose under vibration conditions is to use two nuts. And you jam one against the other, and that puts a whole bunch of friction into the threads so they can't work their way off. Left to its own devices, if you simply put a nut on a screw, making it a bolt, and you have a vibration condition in your machine, eventually that nut will come off by itself, which is why the nuts that hold your wheels on your car are cotter keyed with cross pins so they can't come off, or some other means. I do show a castle nut. That's these grooves that will allow me to put a cotter pin through there with a cross hole in the shaft. Preloading bearings was discussed the other day, and someone asked a question about why you do it and so forth. And after the class was over, I thought I should have used the example of the front wheel bearings on a car. Typically, if they're tapered roller, which they should be, a lot of the modern ones aren't. But if they're tapered roller, they come apart, which makes it easy to assemble. So when you put the wheel on the car, you put the second half of the bearing in, there's a big nut that you bring down to preload the rollers against the races. And the rule of thumb is you take that nut down tight, tight being defined as a man pushing hard on the end of a breaker bar. It's that loosely defined. You tighten the nut, and then you back it off to the nearest cotter pin key, and you stick the cotter pin in. So you give it a little bit of looseness so you don't wear the bearing out prematurely. There also are torque specs for them if you want to be fancier. Washers come in a whole bunch of varieties. I show only a few here. In my experience, lock washers don't. They will usually back out. If there's vibration present, lock washers aren't good enough to really solve the problem. You really need to go to something more definitive like this. This will guarantee that won't come off unless I break the cotter pin. And there are other commercially available. They have these with nylon inserts that actually get crushed when you turn the nut on, and that generates a whole bunch of friction, and those tend to stay on pretty well. But as I said, the best protection is either a cross pin or two nuts jammed against one another. Vibration's a real big problem in machinery. This shows the United National Standard, or UNS, and ISO thread form. One of the few things that the US and the world have agreed upon is thread forms. Not the sizes, because of course everything's in millimeters for the ISO and in inches for us. But at least the shape of the thread is the same, 60-degree included angle. And I'm showing you the US specs here. Unified National is what the UN stands for. C is coarse, F is fine. Here it is here. So there are two series. Actually, there's a third series, extra fine, EF, which you almost never see used. So this is a complete specification for a thread. 1/4 would be the diameter, 1/4 inch diameter, 20 threads per inch. United National coarse, -2A. 2 is the fit, and A says it's external thread. Yes, Michael. It's the OD. It's approximately the OD. The OD will be a little bit smaller than that because the shank of the screw will be the 1/4 inch, essentially. So it's not the pitch diameter. The pitch diameter is something less. So they're standardized on the size hole you put it in, essentially. Right? So that would go in a 1/4 hole. And usually make the hole a little bit bigger for some clearance so you don't have to fight the thing going into the hole. 9/32 or something like that. An interesting aspect of these threads is you would expect that when I load it in tension, you'd figure it would fail at the root diameter, labeled minor diameter there, right? Smallest area. That's where it should break. But it turns out it doesn't. It breaks at a slightly larger dimension or diameter. And this has been proven over and over again in tests. I'm not sure anyone really knows why, but the data are pretty strong. So they've defined as a standard a so-called tensile stress area. And the equation for it is here. So A sub T is the tensile stress area. That's what I'm going to use in my simple equation, stress is force over area. If I know the force I'm putting on the bolt, I know the area, I got the stress. Bingo. So it's the pitch diameter plus the diameter of the minor, dr is called. So it's the average of the pitch and the minor. So it's literally halfway between the pitch diameter, which is an imaginary diameter through here, and the minor diameter. So it's a quarter of the way up the thread, roughly. And for UNS threads, there's an approximate formula there, and for ISO, something a little bit different. So tensile stress is just F over A. Torsional stress is the usual formula, TR over J, which resolves to 16 times the torque over pi dr cubed. Now, this is interesting. The torsional failure is at the minor diameter. Notice this says tensile stress area, not stress area. So in tension, it tends to be stronger than you'd expect from the minor diameter, but in torsion, it's not. So the minor diameter rules there. And of course, it can fail in either mode. And as an aside, in just general comment about fasteners and bolts in particular, is the engineering rule of thumb is, in a machine application, I do not load this type of fastener in shear. That would include, of course, torsion or direct shear. Now, I can't avoid torsion completely because when I tighten the bolt, I may put some torsional stress in it because of friction in the threads. So as I tighten that nut down on the thing, I'm really trying to wind the bolt up because of the friction in the threads. And what you sometimes do is, much like the wheel nut, you get it wound up to whatever you want and you back it off just a smidgen to relieve the torsional stress. And that takes it right, the torsional component, to 0, and picture your Moore's circle. The Moore's circle suddenly shrinks because I took away the torsion. Okay? And that is one of the reasons why you will see a statement in my chapter and elsewhere that says, we haven't quite got to preloading bolts, but preloading is when I put a lot of torque on them before I release the thing for use. And we'll talk about that in detail in a minute. But the rule of thumb says, if I don't break the bolt when I preload it, it will never break in use. And that's really only true if I back out the torsional component. So I take it down to a torque, and you literally can just tap the wrench backwards and relieve that little bit of torsion that's in there, and suddenly the Moore's circle goes boop, because I took the torsion away. And so if I didn't break it then, I should never break it in service. The way bolts are manufactured makes quite a large difference in respect to their strength. If you go buy them at the local hardware store or the Home Depot, you're going to get the lowest quality screws available. Without very much strength, they'll be low carbon steel, unhardened, probably cut threads. There's two ways I can make this thread. I can either stick it in a lathe and cut, run a tool along and cut away the material and leave the shape. I could also run a die on it, which does the same thing, cuts the grooves. That's the left-hand side. And on the other possibility is I make up some elaborate tooling, hardened steel, shaped like the groove, and I set the part up in a lathe, and I bring the tool in. This is not a cutting tool. This is just a wheel, a hardened steel wheel. And while I spin the fastener, I force that tool radially into it until I disrupt the material. I literally flow the material plastically around the tool so that I end up with a larger diameter than I started with because I've pushed material out to make the tops halves of the threads, and the material that I do that with comes out of the grooves. So I'm literally pushing the material around. It's called thread forming or rolling. Now, the interesting thing is, if you look at a micro photograph after you cut those two bolts down the long way and look at a cross section, you can even see it in this low resolution with this lousy slide. On the left, you see more or less a random arrangement of grains, right? Because that's the way the thing came off the rolling mill when it made the round piece that I cut. The one on the right, which has been rolled, you can see, especially in the roots, you can see the contour lines showing up in the pattern. So I've actually made the grains follow the shape. This is what's done with forging, hot forging. That's why forged parts are the strongest that you can obtain as compared to cast or machined from billet. Because in the hot forging process, I'm doing something very similar. This is like cold forging. Because I'm taking a contoured tool and I'm just beating the thing until I get the shape I want, and plastically changing the shape. In the case of a forging, I might have to do that 5 times with 5 different tools to sneak up on the final shape if I'm trying to move a lot of material, and reheating it in between. This is done cold with cold roll steel typically, so I'm just moving the ductile steel. It's you know, full soft, no hardness, until I work it. And when I work it, the hardness increases, right, from work hardening. So I get a double bump. I get a stronger material because I've work hardened it, much like drawing the wire down to small diameters. And I also have a grain structure that follows the contour. So these are much, much stronger. And there's actually a classification scheme for them. SAE, Society of Automotive Engineers, has created this scheme where the grade, as the numbers increase, goes stronger and stronger and stronger. And you will see tables in this chapter on published proof strengths of these various grade bolts. And those proof strengths come about as a result of extensive testing on the actual parts in tension, pulling them to failure, and then they do some statistics on that and so forth, and they publish a strength for a grade 5, 5, 2, 7, 8, and so on. And of course, well, there'll be strengths for 2 and 4 also, but the number of tick marks on the head and their pattern is what defines the grade. And the first 3, as you see, have no tick marks, so they're indistinguishable. So those are the weak guys, and as you go up in number of ticks, you're getting more and more strength here. These look awfully similar. I guess there's one more tick than there. So if you have serious loading on your fasteners, you're going to want to specify. Here's the table I'm talking about right here. So here's your grade number, and here's your minimum proof strength in thousands of psi, minimum yield strength, minimum tensile strength. So there's good data, much like with spring wire and so forth. So we don't have to be as crazy with our sprinkling in of factors here, because these test data were made under the same sort of conditions that I'm subjecting my part to. So now I'm going to talk about how we set the fasteners up to prevent failure. It's a process called preloading, and you may recall when I talked about residual stresses back some time ago, I described how you can preset a spring, or you can somehow build in some compressive stresses with shot peening, where the whole name of the game is to get some compressive stresses into the system that will protect me from tensile failure, which is the fatigue failure mode, right? So what we're going to do here is fool the system into having some compressive stress in it to protect it against tensile failure. But it's a different approach than I described before, where we do something to the material. Here, all we're going to do is take a torque wrench to it and load the dickens out of it. So what I show here is a sandwich of 2 pieces of metal of some sort. They could be the same or different, and they're being held together locally with this bolt and nut and washer. And I'm going to apply some load on this joint. This is a joint right here. And in service, there's going to be some load trying to separate the 2 pieces. So what I'm going to do is clamp it together in a way that will keep it from separating. So we have a length of bolt. We have an LS, which is length of shank. That's the unthreaded portion. And we have a length of thread. And over here we see an L sub T, which is the piece of thread that's in the clamp. So the only piece of bolt that's in tension is between the head and the washer, right? There's some load in the threads too, but this piece out here is feeling nothing. It's out in the air. And by the way, it's considered, and a lot of testing has proven this, the first thread is taking almost all the load. It doesn't distribute well through the threads, so having more threads doesn't really help. Another rule of thumb, if I got a tapped hole in steel and a steel fastener in it, 4 threads develop the strength of the fastener. So I don't have to have any more than 4 threads of engagement, and I will never rip out the threads. I'll fail the bolt in cross section before I rip out the threads. Okay? And that's why the size of the nuts is standardized to be about 4 or 5 threads. I think it might be closer to 6, but some small number of threads in there. This attempts to show what happens when you preload a system. It's kind of a crazy set of pictures I put together to try to get the idea across. The materials we're talking about are stiff. We're talking metal, steel, aluminum, that sort of thing. So when you tighten the bolt with your wrench, or the nut, whichever the case may be, you don't see that metal move very much, right? But it really is getting compressed. So if I put a micrometer across the two pieces of metal that I'm clamping, before I tighten the bolt and after, I would see a difference. Probably a few thousandths of an inch, not very much. So to exaggerate that and make it more visible for the sake of illustration, I've proposed that my material in this case is a spring. So my helical spring represents the material, and my bolt is the thing that's going to compress it and preload it. So really, the spring represents two pieces of material, because this would make no sense unless I had two things that I'm clamping together. Okay, so I'm combining the two things into the spring. So the first thing I do is I put a 100-pound load on this screw by some technique, and thus compress the spring significantly, because it's not that stiff a spring. And I stick in a little piece of metal or whatever, and I capture that deflection, and then I remove the 100 pounds applied force over here. So in this frame, I still have 100 pounds tension in the screw, because I have 100 pounds compression in the spring. Would you agree? So I have preloaded the system to 100 pounds. I have 100 pounds of tension in the bolt, and I have 100 pounds of compression in the material, which is my spring. Now I hang a 90-pound load on this thing. This remains at 100 pounds, because the 90-pound load, being less than 100, isn't able to increase the deflection any. So in effect, the bolt doesn't know I've hung 90 pounds on it. Now, where this really becomes useful is that 90 pounds is doing this. And I'll show you that later on. Because now I'm hiding a good part of the oscillating stuff, which is the bad stuff for fatigue, from the bolt. It thinks it's in static loading, and it's happy as a clam. Okay? So I'm hiding the real situation from it with this preload. It's a simple trick, but it's very effective. But if I now come along and hang a 110-pound load on that guy, more than my preload, my little stop falls out, the thing comes down an additional little bit, and now the bolt feels 110 pounds, right? And the spring effectively feels nothing, because it's going to just extend. So now the bolt's doing all the work, whereas in the previous frame, the material's doing the work because of the built-in load. That make sense? Any questions on this? It's a little hard to understand at first, I think. Okay, let's look at this a little more in an engineering sense. So here I show, instead of springs, a couple of pieces of metal of some sort that are just barrels. They're just cylinders. I'm doing that for a particular reason. So I'm going to put some kind of a load P on this thing that's split side to side to make it symmetrical. And I want to protect this against that external load P, so I'm going to build in some preload to this thing. This just indicates that the standard in the U.S. Unified National Threads is the length of the thread is twice the bolt diameter plus a 1/4 inch. And that's why you don't see the threads going all the way to the end all the time. So if we look at some of the basic equations that apply here, we have a part in tension. The deflection of any tension rod is FL over AE. We learned that a long time ago. F is the load, L is the length of the part loaded, A is the cross-sectional area, and E is the Young's modulus, right? And from any deflection equation, I can create a spring constant equation by just making it be F over delta, and we get AE over L. So that's the classic spring constant of a bar loaded in tension. Now, if I have multiple things in series in tension, then I'm going to have the arrangement you see here, which is what you're dealing with right now in your project, with the combination of the shaft plus the stiffness of the coupling that you're going to buy, plus the stiffness of your motor mount and so forth, are all going to contribute to the overall effective stiffness of the system. So I can calculate these in terms of the dimensions of the bolts and whatnot. So I have to be careful to account for the fact that the threads are smaller than the bolt shank, and I'm going to have probably some threads in the stretch zone. So LT is the length of the thread. That's the piece of the thread that's actually getting stretched in here. Over the area of the thread, now that would probably be the tensile stress area. E of the bolt, and the rest of it is the total length L minus L of T, whatever that is, over the area of the bolt. Now the area of the bolt is a little bit different than the area of the tensile stress area of the thread, right? Because it's really a 1/4 inch or whatever, as opposed to being a little less due to the threads. So I do have to have this 2 springs in series to get the total story. Now, in my simple example here, I've made my clamped material a very convenient cylinder, so I can get the area of that cylinder very directly. It's the area of the material, which would be the donut's area, times the modulus of the material, which doesn't have to be the same as the bolt, over the length of the clamp, and substituting in some terms for dimensions over there, effective diameter squared over 4 EM over L. So I can put a number on K sub M in this simple case. Where this is going to lead us to in the next lecture is when I have a continuum of material and a bunch of bolts, maybe it's a bolt circle around something. How far to the left and right of a given bolt does that clamping reach? Certainly at the bolt, the material's feeling the full effect. But way over here, it's probably feeling nothing. So we have a different and more difficult problem to solve to find out the K of Km, the stiffness of the material, because how much material is actually getting clamped. We'll visit that on another day. That's fairly complex. So that's why I'm making this a real simple problem with just a cylinder. So I've got an expression now for Km and one for Kb. And I can now plot what happens to their deflections when a force is applied to the combination of the two. This diagram takes some study to really understand what's going on. This axis is deflection, delta. And tensile deflection is what the bolt feels, and there's Kb, which is the stiffness of the bolt. And the material will feel compression, which is negative. And it has typically a stiffer spring constant than the bolt. Why? Because it's got more area. Even in my simple cylinder, I've got a big donut of material as opposed to that the donut hole is the bolt and the donut is the material. So the material is bigger, therefore it's stiffer, right? So I'm plotting the slope of the material, the Km, and the Kb. And then I come along and I apply a force. This is my preload, F initial. So I get out my wrench and I start to tighten the bolt, or tighten the nut. You're really supposed to tighten the nut, not the bolt. Tighten the nut. And I crank that force up to something or other, Fi. In the process, if I were able to measure the deflection, I could of the material pretty easily, I would find that it, of course, has to follow that curve, all right? And it ends up with the material compressed by an amount delta M, and it's sitting at A now in terms of load and deflection. And the bolt moves a lot more because it's less stiff, ends up at B, and it has a deflection of delta B. Notice the deflections are not the same when I initially preload the bolt. So now it's static, it's just sitting there, it's got this stress and load built into it. I haven't yet applied my load P. So now I come along and I'm going to put a load P on it. I don't even care at this moment what the value of P is. This is just schematic anyway. But let's think in terms of deflection. It's easy to see what's going on here in terms of deflection. Now, if the following holds true, if I don't separate the joint, and I don't want to, would you agree that when I load the squashed assembly with an additional load, that the deflection of the bolt and the change in deflection of the bolt and the change in deflection in the material have to be the same value, right? If they don't separate. So I've labeled those as delta M and delta B here. So if I put on some load that gives me a delta M, it'll also give me a delta B, and that causes my loading condition to change because that will run down from A to D, and I will now have a new force in the material, which is Fm, right? And by the same token, when the delta B, and these two are equal, that happened, this is the delta delta I talked about. When that applies over here, I go from B to C, and that brings my load up to here, to FB. FB is F in the bolt, Fm is F in the material. PB is the difference between the initial load, Fi, and the load in the bolt. PM is the difference between the initial and the final load in the material, and their sum is load P, whatever I put on it. So whatever P I put on it distributes itself now between the bolt and the material based on the ratio of their stiffnesses. And because the material is typically stiffer than the bolt, it takes the lion's share of the load. And I'm protecting the bolt from failure. I'm hiding the load from it. Okay? Is it making sense? Ask questions if it doesn't. It's a little hard to understand at first, I think. So we can put some formulas on this. The delta delta here is PB over KB. It's also PM over KM. And since I can equate those, I can come up with an expression that relates PB to PM. Remember, the PB is the load in the bolt. PM is the load in the material that results, really the change in load, because there already was some load built in. So think of it as a change in load. And those have the relationship as the ratio of the stiffnesses of the two materials. And the bolt is typically smaller, so PB ends up smaller than PM. And as we saw from that diagram, the sum of PM and PB is P. So with some substitutions, I can make this read this way. So I got KB over KM plus KB, so it's the bolt over the total Ks together, times the original load P. I want to get things in terms of the original load. And I will call this expression KB over KM plus KB, big letter C. That's called the joint constant. So you see, once I know what the stiffnesses of the two materials are, I can calculate the joint constant, C, and that in turn decides how much load is felt by the bolt and how much is felt by the material. And I then have a simple expression to get from one to the other, 1 minus C for the material and just C for the other. So I can now create a separation load, find out how much it's going to take to separate it, at which time the whole thing changes. And I can then have a factor of safety against separation equal to this, and I don't want it to separate, so I want to know what that is. And if I do this for the example I have in the chapter, this is all normalized percent of proof strength against the safety factor for yields. This is a safety factor in yielding, so I don't yield the bolt. Safety factor in separation, they cross at point A, which is about 65% of proof strength. The rule says that we should crank the bolt's preload up close to proof strength to best protect it. In fact, some references will tell you take it to 90% of proof all the time. I'm not sure I agree with that because it's somewhat data dependent. But the numbers typically turn out to be 60, 70, 80%. And I'll do the calculation to find out where these curves are optimal. It's a nice optimization problem.